All right, so let's begin our second part of the virtual memory by going back to the first part. Quick recap, right? So a quick recap. The only thing that, not the only thing, but the main thing that are important here is I'm gonna walk through one example. It's the same example from the last lecture on Monday, so that everyone is basically on the same page. You can watch the video on Monday, or you can watch a quick recap here, right? Right now, if you have an address, and let's assume for simplicity, it's a 32-bit machine, the machine that you can buy from 10, 15 years ago, those like Pentium Pro, Pentium 2, Pentium 3, Pentium 4, like those old chips, they have 32-bit machine, ISA, 32-bit 86 ISA. This is what happened when you have the address. The address essentially is 32 bits. The 32 bits of these, basically they are ones and zero, right? All these ones and zero are broken down into multiple pieces. The first piece is called the page offset. Oops, let me use the pen. So the first piece is called the page offset. Can someone tell me what's the purpose of the page offset? So you have a page, right? This is a page. How big is a page? Right now, if you use Windows or Linux, how big is your page? 4 kilobytes, yes. Basically, if you go to Linux, like the code, the Linux distribution code that are actually the C program that are being written to control this. And basically you see that, oh, it's 4 kilobytes. But one page is 4 kilobytes. What's the typical size of a cache block? Something like 30 to 64 bytes, right? In your CPU, it's typically 64 bytes. 64 bytes is a lot smaller than 4K, right? Which means that given an address, you need to be able to tell, am I accessing this tiny address here or right here? Or am I accessing this part right here, right? A page is like, let's say, think of it as one page in a book, right? In that page, you have multiple characters. The address point to the certain character that you want to point to. So the purpose of the page offset is once you found where is the page that you want to access given the address, so you have the address. Once you find that page, to actually get your data, you need to be able to point to the correct letter on the page, like physically, like in the book, right? So here in a computer, you have a page, you have an address. The page offset is basically used to point to the correct address. The other two pieces of information is basically is for level 1 and level 2 page table. If you talk to people who are not doing architecture, if you talk to people who do who work on the OS computer system, the level 1 sometimes they call this page directory. Level 2 they call it page table. When you design a hardware, everything becomes page table because you can have any levels you want. You can design whatever you want, right? But if you talk to people in software, and that sounds weird. When I refer to software, I talk about like the OS and the system, which is not really like from most people's point of view, those are close enough to the hardware and low level, but they'll sometimes refer to these as page directory and page table. Page directory is basically the first level of my page table. The page table is the next level. So what you do here is when you have these 32 bits, you take away the first 12 bits. Those are page offset. Now you're left with the other 20 bits. The other 20 bits, you divide that in between the middle, right? Right here, this is 10 bit. And this is another 10 bit. These 10 bits, if I have 10 bits of data, How many numbers I can represent with 10 bits? Wake up. How many number can I represent in 10 bits? Yes, 1024. How do you calculate that? 2 to the 10, right? Which means that I can use all these 1024 numbers to point to different index of my table, right? Page table, page directory, those are table. So I can use this number and say, okay, that's row 0, that's row 1, that's row 2. It's like you go through the row on Microsoft Excel. That's the same thing. Basically, if the number here corresponds to, say, 3, right? If this number is basically equals 3, this is what you're referring to. Number 3 will point to PTE3. PTE3 will then give you the address of the next table. This is basically address of the next page table. I'm gonna keep fighting with PowerPoint from day 1 until now. They keep deleting my arrow. All right, so PTE3 will give me the address of the next page table. Why do I need the address? Why do I need the address of the next page table? Yes, you need that. So the answer that your friend is saying is to tell where the next page table is. Why is that the case? Everything here are data. Data, where do you store data? You store every piece of data in DRAM, right? Yes, in the main memory. Yep. So you probably now you might start to get a picture that, hey, the only thing I can do, the only storage unit that I have is DRAM. When you have a computer and you have a program running, the only storage unit you have is in DRAM. This page table basically goes into your DRAM. That's why the page table entry would tell you the address of the next page table. Let's say it's right here, right? In this case, and let's say these bits, this whole thing, index bits, right? Let's say it's correspond to number 4, right? Let's say this is equal 4. Then you will say, okay, I'm gonna check what is in PTE4. PTE4, what will I get afterward? It's basically, well, you can guess. It's the location of DRAM that has my page right here, right? So that I can tell, okay, where in that page am I accessing? Once you have PTE4, the easy things you can do is just grab that value, concatenate the page offset to that, basically put them next to each other, and that's your physical address. This is your physical address. This is your virtual address, right? This whole thing, this whole 32 bits is the virtual address that now get translated to physical address. So let's say I have a virtual address in a 32-bit machine. How many DRAM access do I need to get that data? To get the address, you need 2 access. That's correct. So one of the answers is 2. Is that 2? Let's see, right? Looking this up is 1 DRAM access, right? Everyone is with me. Basically, the first time you need to access that first level page table, because that's in DRAM, I need to go to DRAM, right? So that's 1 DRAM access. This is also 1 DRAM access, right? One more DRAM access because, well, I have the second page table. I haven't got my physical address yet, so I need to look it up as well. When I have the physical address, that's another DRAM access, right? So let's assume I have no cache or what, like, no, not like nothing. I don't have the cache. I don't have anything to cache this virtual address. Then this requires 2 access to get my physical address. Once I have my physical address, I need 1 more access to get my data. Right? Are you with me? Basically, 2 access to get my physical address. Once I have the physical address, 1 more access to locate my data. Any questions about this? Okay, so again, please, that's so for sure, yeah. Page table is in DRAM, right? Are you all with me that page table, all these big table, they are stored in memory? To actually look it up, to actually figure out, okay, to do this translation, to look up the table, it means that I need DRAM access, right? I need to read that table. So every time you go to the page table, that's 1 memory access, right? So are you with me on that? How many page table lookup do I have to do here? Yes, 2. Why 2? You need to, the first lookup is for the first level. Once you have the first level, you look up again for the second level. Once you have those 2 lookup, you get the physical address. Right? You get the physical address. Do you have the data with the physical address? Not really, right? You need to use the physical address to go find your data. That's the third access. So are you with me? Yeah, basically 2 just to get the physical address. Once you have the physical address, then you can find the data. All right. How many people here start to think this sucks? Because if you listen to anything in the caching lecture, we don't want to go to DRAM, right? Not even once. Not even once. So if you do the in-class exercise, you would then realize that, okay, yeah, you don't want to go to DRAM because that's slow. But to have the, okay, so that's another good question. So the question, let me rephrase that again, right? So the question is how to get the physical address from the page offset. Like basically explain this again, right? So once you have whatever values here, right? Whatever values in there, you have that. Then you know whatever value is in here, you put it next to each other. That's basically that's your physical address. Why is that the case? PTE of the second level give you the location of my page, right? Give you the location of my page. The offset basically is being added from that location in order to go to the correct, location of that address in the page. So you concatenate PTE, like whatever value is in PTE4 in here next to the page offset. Yeah, add the whole page offset. Right. So the page offset, if you think about it, page offset is the only piece of information here that's being shared in both virtual address and physical address. Okay. Do you agree with that as well? Basically, the page offset would be in both VA and the PA. Right? So that will come into play in a bit. Actually, is this there are tricks you can do with that information. So keep that in mind. But first of all, when you see all these things, there's a performance overhead that we don't really want to pay, right? Because we want virtual memory to be cheap and magically allows us to do to have like unlimited memory. So as I said, patient with DRAM from our caching lecture, we never really want to go to DRAM unless we really need to. And from the page table structure, we will need to go to DRAM. These conflict with each other. And as a hardware designer, we hate this conflict. We want to be cheap, right? We want to make sure everything runs perfectly without even the software programmer to realize what optimization we do in hardware. So to actually address this concern, right? And let's assume the realistic scenario. In nowadays computer, you don't have 2 levels, you have 4. That's even worse, right? So the first problem, as I said, you can't access your data without knowing the physical address, which means that somehow you need to have the physical address and do page walk. That is slow. The second problem, which we'll cover after we talk about the first problem in more detail, is in modern design, you cannot really access a cache without knowing the physical address. So let's figure out the first problem. Toward the end of Monday, some of you actually guessed, right, the solution here, and they guessed it correctly. Have a cache for physical address, right? Why we have a cache for data? Why can't we have the same similar why can't we use the same concept to cache the physical address? So do you agree that would be useful? I have virtual address, I look it up, yay, I got my physical address. All right. So these thing is called translation lookaside buffer, or TLB. Why is it called that way? The process of converting virtual address to physical address is called address translation. That's why we have the word translation in this cache, right? Lookaside buffer is basically a temporary area where you can take a look and essentially figure out what's my physical address, what's my data. So the main idea is simple: cache the translation data. What do you need to cache? Do you need to cache the page offset? So my first question is, to get the physical address, do I need to cache the page offset? The page offset is in both virtual address and physical address. So do I even need to cache them? I have that information from my virtual address, right? So you don't need to cache them. The only thing you need to cache is called the physical page. Those bits from the PTE, those bits from the page tables for each virtual page. Right? So you don't cache one address, you cache the entire page. These things behave like a cache. If it's used often, they use LIU for the least recently used policy. Have the same structure. You have multiple ways. You have the like a set ID if you want that. You can look up the physical address given my virtual address. This works similar to the L1 cache. And in fact, if you buy a machine, you see that, well, you won't see that, but you will see in the spec sheet, right? That this TLB or translation lookaside buffer on your computer actually have multiple levels, like a cache. You have the L1 TLB, you have the L2 TLB. Because you want to make sure you cache all this translation as much as possible. If the translation data is not in the TLB, that's only when you have to do the page walk. The page walk is to do those lookup to the page table. Otherwise, you magically get the physical address. Any question? Here is the drawing. I'm going to draw it for you for the structure, right? So you have the number page you can have in 64 bits. Yeah, so the question is, can I show once how to find the number of pages we can have in a 64-bit machine? Can you save this question toward the end of the class? Because it's a little bit sidetracked from what we're talking about right now, but it's definitely relevant to this class. Okay, yes. So save that question for, for the end of the class, please. Thank you. Yeah, so you have the virtual address. Right? You have the virtual address. This virtual address, if you break it down, you have the first part. This is called virtual page number and the page offset, right? This whole thing is say 32-bit. You have the virtual page number and the page offset. Virtual page number is anything but the page offset. Basically, whatever bits that are in the non-page offset bits. When you have that inside the TLB, what do I have in the cache? You have the tag, right? What else are in there? You have the data. Can someone guess what goes into the tag? What information do I use for the tag? And at the end, what you want is a physical address, right? Physical address basically also has physical page number and the page offset. So what you want here is basically you want to translate virtual page number to physical page number. So what do I put in the tag? You put in the virtual page number, right? You use that to look up if my page is here, what is in the data. Yes, PPN, the physical page number. Okay. So given the VPN, you search through this tag, right? If it's a match, I get my PPN. Once I have my PPN, I have my physical address because I know the page offset already. Any questions here? All right, so assuming there's no question, if there's a question, feel free to ask now, later, just type in, right? So I'll reply whenever I see the questions. The second solution, this is definitely not going to be covered in many textbook class, but is now on every, like, it's actually everywhere in the chip that you buy. We call this a page walk cache. Anyone want to guess, instead of caching the VPN into PPN, what do I cache now? So page table looks something like this, right? You have the root, the first level to the second level, right? That goes to the third level. The idea is, why can't I just cache? If I know that, okay, TLB, the translation Lookaside buffer, definitely somehow it's not big enough to cache everything. So why can't I just cache part of it, right? So the idea is to cache just part of the data. Each page table structure, if there are common page table, cache them. This is called page walk cache. So instead of caching the VPN into PPN, now you cache the page table entry of commonly used data. So the benefit is this allows higher coverage. You can actually cache more things, right? Because you only cache the lower level page table, but then this you still need to do some translation. You still need to go to DRAM a few times. Let's say you have four level. Let's say you have four level of page table like this, right? Here's what the page walk cache would do. Okay. So this is level 1 page table, level 2 page table, level 3 page table, and level 4 page table. What you got here is if you have a TLB cache everything here, right? Everything from level 1 to level 4. Basically, you start with VPN, you magically have PPN. If you look at the page walk cache, what you're going to get are part of it. Let's say, for example, you might get from level 1 to level 2, right? So you can skip the first level, the second level. Then you get the address for the third level, which then would reduce the amount of time you need to go to DRAM from 4 to 2, right? These allow better coverage because if you just cache this part or this part, you cover basically most of the address, right? Most of the address would have information that are covering the first and the second level because they share. And then for the third and the fourth level, you still need to do page walk, but doing it twice is better than 4 times. All right. Okay, so let's go to the next set of topic, which is let's pair up virtual memory and cache. The data cache that we talked about 2 weeks ago. That, okay, we have a data, you want to access the main memory, you better put things in the cache. That is a little bit of a problem when you bring in virtual memory, and I'll tell you why, right? Let's think about the tag and the index bits in the cache. So what is a tag and what is the index bits, right? If I have my address, where is the index bit? So this is the byte in block, right? This is the index bit. And the rest are the tag bit. So this is from our caching lecture, right? Everyone with me so far? If you have an address, I want to look it up in the cache, I would find the index bit. The index bit tell me what? What does the index bit in the address tell me? It gives me the set ID, right? This gives me the information if, oops, is in the cache, right? Are you with me so far? Basically, if you have an address, you want to look up that address in a cache, then you can look at the set ID using the index bit. You know the set. Once you know the set, you search way 0, way 1, way 2, way 3, way 4, and see if the tag match. If it's matched, data is there. I never said whether this is a physical address or virtual address, right? I never said that it's a physical address or virtual address. So if you use virtual address, basically if the virtual address is the address you use in a program, right? Then essentially this is the virtual address. The address that you have is a virtual address, right? What is the problem with your virtual address when you use the tag? Let me rephrase the question. Is it possible that I run 2 programs and they have the same virtual address? If I run 2 programs, can I have the same virtual address? Maybe, yes. That's a great question. That's a great answer. It's actually true. Maybe. It might. It depending on what luck we will get, right? It's possible that I will have the same virtual address. Are those virtual address mapped to the same data? Actually, yes and no. Sometimes you have the virtual address that are the same from two programs. They go to different piece of data, right? Because of the memory protection, virtual address is locally inside the program. You can't say, right? If you think about it a little bit more, so in that case, if you just look at the tag, can I use the virtual address as a tag and then guarantee that it's my data? Okay, it's possible to have, okay, let me put it this way. If I look at the virtual page number, so if the two program has the same VPN, what happened? I have the same tag, right? I would have the same tag if the two program has the same VPN. So basically the reason I said that is, one of the friends here said, no, because if two program has the same VPN, and that's correct, right? You can have two programs that go to the same VPN. The same VPN doesn't mean that it's the same page, right? It doesn't mean it's the same page. It doesn't mean it's the same data. But because of my tag, right, because of the tag, it's possible that I ended up with the fact that the cache say, hey, that's my data, right? So it's possible that you have the virtual address that looks the same, but it doesn't belong to you. And the cache in this case, if you use virtual address as a tag, then you're screwed, right? Any question about it? Basically, then you're screwed because you can't tell whether it's your data or is another program's data. So if you think about it, a little bit more, right? You have the index bits and you have the tag bits. You can essentially say that, okay, I can use the index bit, the VA or the PA for the index and the tag bits. How many combinations do I have here? 4. So let's talk about each of these in detail. The first combination, I use physical address for everything. This is called physically indexed, physically tagged. I can use physical address for the index, virtual address for the tag. I can use virtual address for the index, physical address for the tag. And then I can use virtual address for the index, virtual address for the tag. Some of these will give you different problems. The first problem I'm going to talk about is called homonym problem. What is the homonym in English dictionary? It sounds the same, exactly. So what does in computer, one thing I can say is like, okay, it sounds the same. Why? I have the same virtual address, but it's actually going to the different location because it's from different program, right? That's why we call it homonym. This means that if you want to look up my cache, my data in the cache, I need to be able to tell the difference between the two, right? I need to be able to tell the difference between virtual address of Chrome versus virtual address of PowerPoint versus virtual address of the game I'm running. Another problem is called synonym. It's essentially when two virtual address get mapped to the same physical address. Right? It can happen as well. You have shared data. It doesn't mean that Chrome never share data with other processes, right? So you can share the data, but now you have two virtual addresses that map to the same physical address. Now the tag, again, need to be able to tell the difference between the two, right? So otherwise you fetch the wrong data. At the end of the day, if you think about it, index bits in the cache is to tell what set am I looking at. The tag bit is the important ones to get the correct data, right? If the tag is the same as that should be the same data. So which one of these four would have the homonym problem? Which one of these four would have the homonym problem? Homonym problem is so one answer is 1 and 3. Anyone agree with 1 and 3? Anyone want to guess 2 and 4? Or anyone want to guess 1, 2? Or anyone want to guess 3, 4? Okay, one answer is PIPT 3, 4, and okay, awesome. Now we get every single combination. And none of them are complete and correct. So it's good. Please keep answering. I think this is basically how we can keep the online format a little bit better. Basically, homonym problem is when you have the same virtual address and you don't know who the data belongs to, right? So if you use the virtual address as a tag, which is here and here, you're gonna have the problem because you use the virtual address, but the virtual address can't tell. It cannot tell who the data, like this data, is it belong to program 1 or program 2? So option 2 and 4 run into the homonym problem. All right, so we can kick them out. For the same beta, both tag and tag bit need to be the same, right? Yes. So that's a great question. The question is for the same data, both the physical address and the tag bits need to be the same. Yes, it is. That's the actually that's kind of like the requirement that you should have, right? So we can kick out these two options. In modern day computer, there are actually now a lot more proposals to use VIPT. We will not talk about this. Let's say that okay, we are not using VIPT, we are not using PIPT for now, just for the sake of have an easy solution against homonym problem. If you are curious about like super high performance computing and new hardware design, talk to me. At the end of the day, this knowledge is like, okay, this is the canonical traditional way how to build things, and this is actually on most of your computer. Doesn't mean that you can't fix it. But now let's look at the other two options, PIPT and VIPT. The first thing is, what would be the issue with PIPT? What do I need to get the tag? And what do I need to get the index? You need to get the physical address, right? You need to get the physical address just to access my cache, right? Because you need the physical address for the index bits and you need the physical address for the tag bits, and you magically would need to get both, right? So that can take some time. Do you agree that can take some time? Basically, you need to get the physical address before you do anything with the cache. All right. What about VIVT? VIVT, we talked about it along 2 slides ago, saying, hey, you have homonym, so let's not use it. Right? You can run into homonyms. This is a paper that say, okay, actually, it's not too bad. There are ways to go around the problem. I'm not gonna ask you to read the paper. I'm not going to expect you to read the paper. I just want to let you know, hey, it's not the end of the world. It's possible. You can actually design around it. What about VIPT? What about VIPT? Why is using the index bit from the virtual address okay? Anyone want to take a stab, take a guess? Why is this not too bad? So what do I use the index bit for? What do I use the index bit for? Yep, to get the set ID, right? To identify the set. You are not using it to identify the data. You just to go like, okay, it should go to that set, right? So as long as your virtual address is the same, you are going to go to the correct set. Do you agree with me? As long as my virtual address is the same, I would get to the correct set, right? I'm not using it to look up whether I have the data or not. I can use it to say, okay, that's the correct set. Then you can use a physical address for the tag. This get around the homonym problem. This basically allows you to say, okay, this is my correct data for sure. Guarantee this is correct data. You can use the virtual address for a set ID, and then you can use the physical address to check the tag. You might be asking, what is the benefit of this? It seems so minor, right? It actually provides quite a bit of benefit, right? Why is that the case? If you do PIPT, this is the process. You have virtual address, so this is PIPT. You have virtual address, right? You first need to get the physical address. You use the physical address to get the set, right? Once you have the set, you will get the tag, right? This also gives you the tag, and now you compare if it's equal, right? This tag and this tag. If it's a yes, cache hit. If it's a no, it's a cache miss, right? So you first need to get a physical address to get a set to compare the tag. This is VIPT. You have virtual address, right? You have virtual address. Oh, okay, that's a great question. Why is virtually tagging so problematic if there's only one VA for one PA? That's actually not really true because you can have one VA from two programs that go to two different PA. Right? Basically, it goes to two different PA from one VA from two programs. So that's why it's a problem, because if you use VA as a tag, you can't tell the difference. That is actually the idea of the paper that I just talked about. We can then assume that that case never happened. The paper talk about these days you have big memory, right? So you're not gonna run into that case a lot. So you can actually guarantee that from the system. If that's the case, then you can use VIPT and that's fine. And VIPT, you use virtual tag and virtually index, then perfect. Yeah, you just kind of like propose an idea from the paper. So if you can guarantee that a virtual address will uniquely go to one physical address, then you can use VIPT. Right now, let's assume that you can't do it. All right. Doesn't mean it's impossible. Yeah, that's a great question and great answer, actually. That you have said, hey, but we can keep it that way. Yep. Okay, so you have virtual address, right? The virtual address would then be used for the index. And now you use it to get the physical address. So this is the set, right? So you get the set ID. From here, you get the tag. From here, you also get the tag. So you do the compare. Yes, it's a hit. No, it's a miss. If the comparison is not the same, then it's a cache miss. This saves you some processor cycle because you can access the set while you're doing the translation. If this thing is a TLB hit, it usually takes one to two cycle, right? It's fast. TLB is fast. So if that's a hit, then you can save time to get to access the cache. That's why this is important. If that's not a miss, if that's not a hit, if you try to get the physical address and it's a TLB miss, then yep, you're screwed. You need to do page walk. That is why more and more people are trying to figure out, can we use VIPT? Because if you can use VIPT, we don't need to think about translation whatsoever until you need to go to DRAM. Right? So, and that's the key argument from the paper that I said earlier that was published 2 years ago, actually. Okay, so that is all for pairing up virtual memory and the cache. But before we kind of move on to the next topic, let me put everything together. Over here, let's say this side you have the CPU. You have load store. Basically, you have memory access. Load and store, things like that, you have. What does a load and store give you? You get the virtual address, right? VA. Over on this side, you have DRAM. With me so far, you have the CPU, you have DRAM. You want to get data from DRAM. You start with the virtual address. Are you with me so far? I'm going to draw everything and tell you what is going on in your computer. On the top part, I'm going to talk about the cache. On the bottom part, I'm going to talk about what is going on the virtual memory. So this is the cache. This is the virtual memory. So what's in the cache? L1, L2 cache, right? That's it. Simple. So let's say this is L1. This is L2. Then you go to DRAM afterward, right? Let's say this is the data part, and this is the tag part. So what do I put in the tag part? Do I put the virtual address or physical address for the tag? So yes. So for the index, we use virtual address. For the index, we use virtual address. My question was, what about the tag? Physical address goes in here, right? So you get physical tag. Yep. In the L2, because you have to use a physical tag anyway, can I just use physical index? You can use it, right? Because by the time you are done with L1, you got the physical address already, right? You need the physical address already to go to L1. So by the time you're in L2, you can use the physical address. You can keep using the physical address. That's fine. What about this? What do I use? VIPT, right? So what index bit, is it from virtual address or is it from the physical address? index bit, virtually index, physically tag. So hopefully that's a hint enough, right? Virtually index. I use virtual address for the index. So index is the part of virtual address. Are you with me so far? Basically, use the virtual address to find the index bits. Then for the tag bits, we use the physical address. With me so far? So far? Yes, yes, no, yes. No? Okay. For VIPT, let's assume that we have both the virtual address and assume that we know what the physical address is given the virtual address. On the caching side, I will use virtual address to find my index bits. Then, to find my tag bits, I would use the physical address. Assuming that we have both. Because we will talk about virtual memory right after this. So are you with me so far? Yes, no, okay, yes, yes. Okay, yes, okay, cool. So that is assuming that we have physical address. So let's talk about how to get physical address. So you have virtual address right here, right? To get the physical address, what's the first thing I'm gonna check? What is that cache for physical address? What's the name of that structure? Yes, exactly. You look it up in the TLB. Right? If it's a hit, you use this. It goes right here as a tag. I can't draw again. I hate PowerPoint drawing. All right. Basically, if it's a hit, you then get your physical address. Physical address can be now used into searching the tag in L1. Are you with me so far? If you have a TLB hit, you get physical address. So you can look up in the cache, whatever you find. That is when you have a hit. All right. What if this is a miss? Yes, the end goal. That's a great question. Aren't we looking into DRAM, right? That is the case. You have the virtual address. The only thing we want from this line of code in my program is I want my data. My data is in DRAM. So are you with me so far? Basically, I have a virtual address. I just need my data. I have an address. I just want my data. Right now, my data is represented using virtual address. The first thing I'm hoping for is, okay, I'm hoping that my data is in the cache. Right? It's in the cache. To get that data in the cache, you would then need the physical address. Right? You would then need the physical address. To get the physical address, hopefully you hit in the TLB. Are you with me so far? This is my end goal. This is where my data is. Okay, yeah, my end goal is hopefully at some point I got my data. All right, right now we take care of the case that if it's a TLB hit, you got the physical address. When you have the physical address, you can check, is my data in the cache? Is my data in the L2 cache? Is my data in DRAM? Perfect for now, right? What if this is a miss? TLB miss means that we don't have the physical address yet, right? What do? This is a process called page walk. Right? So over here, you have page table. I will just call it PT, page table. Right? So you have a bunch of page table in DRAM. And when you do page walk, what happened? Let's say this is your current machine, 64-bit machine. How many levels do you have? 4, right? So look up for the first level, again for the second level, again for the third level, again for the fourth level. The fifth time you have the physical address. So let's say right now you have the physical address. After you do all this page walk, you go to DRAM 4 times. You have the physical address. What do you do next? Once you have physical address, what do you do next? End goal, I just need my data, right? So yes, you basically you want to get the data from that address. So the obvious thing is go to DRAM, right? But because cache is faster, this physical address go here. I finally got my physical address. Is my data in the L1 cache? Why do I go to L1 first before I go to DRAM? Anyone want to guess why? Basically because going to L1, if it's a hit, it's faster. It's a miss in the TLB. It doesn't mean that my data is not in L1. The L1 cache holds the data. It just happened that I don't have the physical address to check. And yes, because in case it's in L1, this is still faster than going to DRAM, right? So hopefully this gives you a big picture on how tedious things can be depending on the status of whether you have the translation. Oh, okay, that's a great question. So the question is, where's the PIPT, VIPT, PIVT, VIPT in here? For this figure, we assume VIPT. For this figure, we assume VIPT. Basically, VIPT means that I would use the virtual address for my index bit and the physical address for the tag bit. It's a little bit faster than PIPT. Basically, VIPT and PIPT, when you use physical address as a tag, that gives you correctness. It gives you correctness when you boot your machine. Physically indexed is a little bit slower than virtually indexed. So if virtually indexed is strictly faster, why don't we just use virtually indexed physically tagged? Because it's the best of the 4. Right? Basically, that's the argument. It's the best of the 4. It gives you correctness and it's the fastest. So we assume it. All right. Any questions about this? The reason why I have this putting everything together slide is it happened to me when I listened to this same lecture when I was a CMU student as an undergrad. I don't think the professor did a good enough job pairing up caching and virtual memory. So I want to pair both of them up. You have the virtual address. Basically, this is what you want. You have the address, you just want the data. And this is the path that you need to take to get the data. If everything is a hit, magical, right? You go to the TLB hit, you go to the cache hit, yay, fast. If it's a cache miss, yeah, a little bit slower. If it's a TLB miss, nightmare, right? You go to DRAM many times. Any more questions before we move on to the last topic today? Okay, the last topic is pretty quick. We call this page fault, right? We said that virtual address can give you virtually bigger than DRAM memory, right? Which means that some pages will be in hard disk, like all this hard drive that you buy. So what if the page that we want to access is not in DRAM? This particular instance is called page fault, right? And to actually resolve page fault, you need to get that from storage. Unless you want to dig into a storage system class, because this has a lot to do with additional coding, just assume that this takes so much time. Going to DRAM is like hundreds of nanoseconds. Like you still talk about nanosecond level. Going to storage is microsecond. A lot slower, right? So you don't really want this. This is out of the scope of this class. I just want to put it here for completeness. If you take like a OS class, it might be being discussed here again, but it's still a pretty advanced topic because we talk about homonym. We haven't really talked about synonym. Synonym is when two virtual address go to one physical address. There are a few solutions. I'm just going to briefly talk about it. Not going to go into much detail unless you want to take an architecture class, then we'll go into a little bit more detail. But essentially, you can kind of limit the cache size so that the index is from the page offset. If the index bit come from the page offset, right? If the index bit is from the page offset, what do we know? We know that virtual address has the offset. Physical address also have the offset, right? So if my index bit is from the page offset, you're fine. You get one physical address. Yay, right? Why is this an issue? If I have two virtual address, right? If I have two virtual address that map to one physical address, it's the same piece of data. You have shared data between two programs, right? It's a shared data. If the index bits come from the virtual address part, it's possible that my set ID is going to a different set, right? It is possible because you have two virtual address, you have no guarantee. Another solution is you can do something called page coloring, which the key idea is essentially make sure that the index bits of the virtual address part is the same as physical address part. If you want to follow this up, drop by office hour. I'll kind of dive into detail. These are not going to go into your exam. These are not going to go into your exam. It might be on a computer architecture exam. It is about like that kind of level of the information. The last benefit is what I define as memory protection. Basically, it allows two program to basically prevent two programs from accessing each other data, right? So we talk about this status bit. Right? Anyone remember the status bit in the page table? Status 0, status 1. That is like read and write. The last access bit, the dirty bit, the supervisor versus user bits, right? These things being basically when you go through the page table, we check this thing to make sure that you don't violate any constraint over there. At this bit, one thing that they include, we call this address space ID. Oops. Address space ID. I can't. Okay, I think I just broke PowerPoint. I can't do anything here. All right, I'm just gonna use a laser pointer. What? Give up on using my pen and PowerPoint. Basically, these bits can include the address space ID bit, right here. I can use my finger still at least. This, think of it as a program ID, like process ID. They'll be put, it's not exactly process ID, there are way to make it shorter. But basically, you put it there to make sure that you know who owns the page, what program owns the page, and is this a legal access? So you can check things like, is it a read and write or read only? Is it the user or supervisor, right? User is your account, supervisor is sudo or root, right? So at the end of the day, these allows safe access to all the addresses. This is the main big benefit of virtual address that you still use today. That's why you can't really get rid of virtual memory. It's just a matter of like, how can you make it faster? That's it for today. One quick thing. I just realized, thank you so much for letting me know. Otherwise, I would subconsciously have lecture on Monday. I did not know that next week, Monday is another holiday. How many holidays are on Monday or Wednesday? I don't know anymore. It's so many. But yeah, it's a holiday. Go take a break. And I guess based on your condition right now, go catch up with all the homework. It's sad for me to say that. Actually, it sounds so sad. Hopefully you catch some breaths and take some break as well, right? There'll be a makeup review session as usual with all these like class conflict. Right now, we are basically done with SysQ material. Anything afterward are things that I find handy, things that I find like, okay, these are good to know. It's system related, and hopefully it motivates you to either like, okay, maybe OS can be interesting, maybe architecture can be interesting, maybe things like database system can be interesting for you in the future, right? Depending on how you want to progress in the class. Review session on Friday, another review session right before the final exam. So there'll be more review session just so that I want to make sure that I answer every one of your questions. Are we going to have a makeup class? Yes, that's a great question. Makeup class is on Friday. It's online. I'm going to post on YouTube. When is our final? I need to check the MUIC calendar, but I believe that's around in the middle of July. Yes, that's a great thing. That's a great question. So one of the question is, can I give an example of question for the final? I regret I did not do that for the midterm. I'll do it now. Okay, so if it's a week of 24th of July, so basically it will be before that week for the review. And the final is basically, I'm gonna open a vote for you, whether you want it on Monday or Wednesday of that week, right? And for those of you, I don't know why no one exercise that possibility. The format, okay, one question at a time. The format of the final is going to be partly written, partly might have some coding depending on how I can deal with like this caching and virtual memory, because I think those have to be written exam. I would still need to think about it, how to make this work with the online format, right? And I don't want to, basically I want to make sure it's a final week, and I have a gut feeling that everyone would do like 24 hours take home exam. So I don't want you to run into the case that you ended up doing 5 short assignment in a back-to-back like 24 hours period, or you die, right? So I'll need to think about this a little bit. The other question is, when will the next assignment be released? Actually, that's kind of follow up from my assignment 3. So I am going to release it on Friday. You will have until the last Friday, right before the final week. You will do some cache simulator for the last assignment. This is going to be a brand new assignment. No one's seen it before. So hopefully it's fun and it's not too hard. I need to check the calendar, and to be frank, I have not checked it, so let me check it right now. Yep, I'll follow up on another one of the question, which is when is the last day for assignment 3. So trimester, last day of class is 18th of July. So basically you have until 18th of July for assignment 4. And then when is 18th of July? This looks kind of weird. Is that a Saturday? Yeah, that's not good. So for assignment 4, I'll give you until the 21st of July. Kind of like the last day I can do before I bomb like grading. So I think the final is either 20th or 22nd, the Monday or Wednesday. That is really important. Please check with me personally because this is also related to your health as well, right? So please check with me. It's not like please check with me. Prioritize your own personal health. You have a solution. For the in class, I think I put it like as late as possible. Don't worry about in class. It's like after the final. Yes. Okay. So assignment 3, a couple of things. Only 3 people submitted so far. And about like 5 more people are asking me how to log into SysQ in the past 4 days. So it got me worried, right? Because if you haven't really logged in, you haven't got the starter code, and it means that you haven't started. Which kind of bummed me out to some extent because at some point, I think 3 weeks ago, I asked everyone to log in and test it. If it doesn't work, let me know so that we can actually resolve it as soon as possible because I said assignment 3 involved this. But I'm gonna still give you some option. If you submit it, if you look at assignment 2, I give you 10%. This time I'm gonna give you 20%. I really appreciate people who start early, people who finish it, right? You will get rewarded. So your extra credit is 20% on top of the grade that you get. You have until Friday. For those of you who want an extension, I'm not gonna give you a lot of extension this time. I have to be honest here. I'm a little bit upset on the fact that not many of you start until the last weekend, right? You have 2 weeks to start. You choose to start 4 days before when it's due. So you have until Friday to finish assignment 3. That's final. I'm not gonna extend it. You can use the late day token to extend it to Saturday. Yes, if your code doesn't work perfectly, and if you believe that if I apply the 20% extra credit on whatever score you get, it's going to be better than the Friday submission, keep your code there. You don't. That's why I put the more extra credit this time because I have a gut feeling that many of you are still need to finish it. So not a lot of people finish it right now, but I do appreciate people who finish it on time. Right? Canvas is fine. SysQ, I would appreciate it because at the end of the day, I'm gonna transfer everything to SysQ. Percentage about each assignment is like this. Assignment 1 and 3 is an equal percentage. Assignment 2 and 4 would have more. Because assignment 2 and 4 will be a little bit longer and take more effort compared to assignment 3 and 1, right? So let's say it's out of 60. Let's say, oh, no, my bad, I did the math wrong. Let's say everything is out of 100. Let's say everything is out of 100 and I'll scale it to how much assignment is worth, right? Assignment 1 and assignment 3 is going to be 20 points. Assignment 2 and 4 is 60. 30 each. So at the end of the day, it's add to 100, 20, 30, 20, 30. assignment 1, 20, assignment 2, 30, assignment 3, 20, assignment 4, 30. That adds up to 100. All right, so does it answer your question about the percentage of each assignment? Okay, awesome. Yeah, so that's where things are. I would actually try my best to release assignment 4 as soon as possible, but I have a committee meeting for a conference on Thursday night from 7 p.m. to 9 a.m. the next day. So I think I'm dead like on Friday. I'll try to do it as soon as possible, but I feel like I'm gonna be pretty dead on Friday. The makeup class? You mean the makeup class for the review? So so what do you think if I put the makeup review session for the makeup class on Saturday afternoon? Because I figured no one had conflict there, but that kind of invade into your like weekend, right? So up to you. I don't mind. So if you think that's better, I can do that. Let me send a poll, right? Let me send a poll to do the makeup class, whether it's on Friday or Saturday. Uh, at the end of the day, I'm gonna post the video, and then it's just a review of everything. So if you still have questions, you can ask it during the next review session or during the office hour. Right. So I'm gonna have office hour again, like usual, 7 p.m. today. I kind of guess that it's going to be flooded with assignment 3 questions. So if you have questions on assignment 3, come in. Don't ask me what's the answer to get the counting number of bits. I can't give you the answer. I mean, I can't give you the solution. Awesome. Okay, yes. Thank you for reminding me that. So this was back in the beginning. Can I show how to find the number of pages that we can have in 64-bit machine? Let me give you a more like how can I find the number of pages in any number of bits. All right. So you have an address, right? Bit 0 to bit n. So let's say I have 4 level of page table. This is the page offset, right? This is the page offset. This is level 4, level 3, level 2, and then level 1. I can draw again, level 1. All right, you have n bits. Let's say this is A bits. This is B bits. This is C bits. This is D bit, and this is E bits. How many different number I can represent with A bits? 2 to the A, right? 2 to the A. This is 2 to the B. This is 2 to the C. This is 2 to the D. Are you with me so far? Yep. And this, it means that I can represent 2 to the E address. Right? 2 to the E bytes, essentially. With me so far? 2 to the E bytes. I just want to make sure at the end I get number of bytes. So how many bytes can I represent with all this? The answer is I can multiply everything here, right? This is number of bytes. This is the maximum number of bytes that I can store with this virtual address with n bits. What is this number? 2 to the A plus B plus C plus D plus E, right? What is A plus B plus C plus D plus C? It's n, right? So in the maximum case, for each program, because each program has their own virtual address, for each program, you can have up to 2 to the n. Any questions so far? Basically, for each program, you can have up to 2 to the n. The way you can look at this is, I have A bits for the first level, B bits for the second level, the C bits for the third level, D bits for the fourth level. So in total, I would have 2 to the A plus B plus C plus D for each page table entry. That's my page. Then you multiply by 2 to the E, then you get the number of bytes. Doesn't mean that you will need to use every single bit in the virtual address. Given the 64-bit machine, 2 to the 64 is a lot, right? So definitely way more than enough. With the current technology, like I don't think we'll end up with petabytes of DRAM soon. We are at around terabytes of DRAM at the moment. Terabytes of, I guess, memory at the moment, but you are not going to like petabyte in a while. And this is coming from a guy who worked on DRAM, right? So yeah, it's not easy to scale. That's why I said it's a maximum number. Does it answer your question? So yes, so you can basically have 2 to the n bytes in DRAM for a program, for one program. Because that's what you can have in the virtual address in one program. So let's say you have 10 programs, you can actually have 10 multiplied by that number. Oh, okay. So finding the number of pages. Number of pages that you can handle, you cut out the 2 to the E, that's number of pages you can have. The bits in each level, that's a great question. The bits in each level is variable. Yes, it's by design choice, right? So if you go to the Intel manual, it would tell which bits goes where. Which bit is for the first level, which bit is for the second level, which bit is for the third level, which bit is for the fourth level. So this is for the hardware designer to like, hey, this is probably the best mapping. So let's do it this way because we find that we run 1,000 different programs and this is probably the best. Most of these are pretty empirical and observational. Like we run multiple programs, test it, and we find the combination work best for most program. Okay, question about the assignment. The question is, you get confused about copy the zip file to the directory. If you submit the assignment on Canvas already, don't worry about that. Just make sure it's either on Canvas or on SysQ. If basically at the end of the day, I'm gonna download everything on Canvas, put it on SysQ and do the grading that way. I would appreciate it if you can submit on SysQ on a hand-in folder as well. That give me some less tasks to do. All right, so the question is about VIPT. If PT need to be translated from virtual address, then VI is virtual. Doesn't that not need. Okay, so that's the point about the benefit of VIPT. And basically, VI means that you got the index bit right away because you have the virtual address. Then you get the physical address to compare the tag. It just happened that if you can search the set ID first, if you can search the set ID first, it turns out to be faster. That's why VIPT is a little bit faster than PIPT. Yes, it's another thing that's being done by design, and there's a reason why this is faster, right? Because you can use the set ID to get the collection of tags. That takes time. You basically you extract the set ID to get the collection of tags. Hopefully, at the same time, the virtual address gives you the lookup from the TLB. Now it gives you the tag. So once you have the set of tags from the set, hopefully at the same time you got the tag, the correct tag from the physical address, and you can use it to look up your data. The question about submission, yep. Submitted on SysQ mean basically, yeah, copy to that folder. That's all. I gave everyone the right permission. So you should be able to write to that folder. Once you write to that folder, you can do whatever with your own like ID folder. Just to make sure, submit on Canvas as well, just to make sure. One thing I would definitely appreciate is when you submit on Canvas, put in your user ID, like your Mahidol University ID, so I can pair up like your ID with your name. Oh, actually, I can get it from Sky, so don't worry about that. But yeah, if you do it, it saves a little bit more work here. You should see how different will be for the 3 other ones. Okay, yeah, sure. That's a great question. Let me. I think I need to draw it. So let me save the annotation and drawing here for now. I'm gonna create one more slide so I can draw this one for you. All right. Okay, so do you see my slide that say VIPT versus PIPT? I'm gonna get rid of the virtual tag for now because virtual tag this is not correct. I think like it can be done to give the correct answer, but it requires additional assumptions. So I'm gonna compare the performance of VIPT versus PIPT. Oops. The in-class exercise will come out next week because the next in-class exercise, I want you to focus on the, I want you to focus on the virtual memory part now that we have the exercise on the caching part. Right. So here, let's assume the left side is PIPT and the right side is VIPT, right? We have the virtual address, right? If I have a PIPT, what's the first thing I need to do? Translation, yep. That give me physical address, right? Physical address would be used to look up cache set, right? So you get the cache set, right? Once you have the cache set, you use physical address again, right, to get the tag. So virtual address get physical address get the cache set, right? Because it's physically indexed. You need physical address for index bits. Then you get the set. Once you get the set, you use the tag to compare and see if the data is in the cache. Over here, what do I use for the index for VIPT? Virtual address would give you the set, right? At the same time, I would translate to get the physical address. Are you with me so far? Basically, the part that I go grab the cache set and the part that I go grab physical address happen at the same time. It's done in parallel. With me so far? So you use virtual address to grab the set. You use virtual address again to grab the physical address. Once you have the set, the next thing you need to do is to check the tag, right? So once you have physical address, you have the tag, right? Check if it's equal. If it's equal, you get data. So it is a little bit faster. That's what I meant, because you can go get the cache set at the same time as getting the physical address. Once you have the tag and the physical address, you compare them. Does it answer your question? PIPT, PIPT is the same performance as PIPT. Why is that the case? To get the set, you need the physical address, right? So you can't even, like, even though you have the virtual tag, without the physical address, you can't get the set. So because the first thing in the cache, you need to get the correct set, right? So that's kind of like the worst of everything. For VIPT, that is the interesting part, which means VIPT is basically, hey, we don't need physical address. Cache lookup is done using the virtual address. That's fast, right? You can do everything in parallel. You look up the set using virtual address, then you use again the virtual address for the tag. You get the data. The concern is that data might not belong to you. That data might not belong to you because you use virtual tag. Which is why I really love one of the comments here during the class, like during this class, that suggests that what if you make that assumption that we never have the virtual address that map, like two virtual address that get the virtual address that get mapped to different physical address. It means that you can use VIPT, right? It means you can use VIPT. So that's possible. It's possible. The reason why I'm not going to cover that more in detail is it is a little bit out of the scope of the introduction to computer system. And I would love to talk more about it. So if you want to ask more questions about that in the office hour, yeah, I would definitely love it. Another great question. Is first assignment graded yet? I'm on it. Hopefully by this weekend. For the first assignment, hopefully by next weekend for assignment 2. And yeah. Yes, we will keep using C. But I'm not gonna, so the next assignment, I'm gonna leave it pretty open-end in a sense that I'm not gonna force you to use like, hey, use this data structure, use this pointer. it will be pretty open-end. Use whatever you want in C to make it work. This way, you allow to use array. You allow to use pointers. You're allowed to use anything you want. And hopefully this gives more of the design option, right? And the part I'm gonna ask you to compete against each other is to come up with some creative policy for our cache. All right. Any more questions before we conclude the class today? So I seriously hope that you see the bigger picture where you have an address. Now you know that it's a virtual address and you know how it works along with the cache. That's it for today's lecture. Thanks for joining and asking a lot of questions. I actually love this lecture. Actually, it's pretty fun, at least from my side. Answering all your questions here. I love it. I think it's really creative. And assignment 4 is so that's a great question. The answer is my goal is it will be a little bit less of a coding and a little bit more of a thinking about how cache works and make sure it followed that logic. So a bit less of a coding and more of a designing and making sure you have a proper design going into each of the functions I would like you to implement.